All right, so this is the first of the last couple lessons in this unit, in which our focus becomes on looking at rational equations instead of expressions. So what's the difference? Well, a rational expression is what we've been dealing with for the last several lessons, and an expression doesn't equal anything, in essence. There's no equal sign. It's just, in this case, x over 2 plus 3. And what is x? X can be any number. You can, x, in this case, there's no restrictions, so x can be any real number. Or if you want to use the fancy notation, we can say x belongs to the real numbers, which means, you can pick any number you want for x, and then go divide by 2 and add 3. That's an expression. In this case, x can be anything. It doesn't equal anything, and that's what we've been kind of focusing on for the last several lessons. An equation, well, has an equal sign. And an equation, there's a left and a right side that equal one another. And in this case, x cannot be anything. In fact, far from it. In this case, x can only be a certain value or values, which means the vast majority of numbers you pick. This will not be true. If I just pick a number, 1, well, come back here. If I just pick a number, 1, if I replace x with, I said come back here. If I just replace x with 1, I don't have the same thing. On this side, I have 1/2 plus 3, which is 3.5. On this side, I have 2 plus 3/4, which is 2 3/4. Hate to tell you, those are not the same number. And so, again, if I just pick a number for x, this equation will probably not hold true. And that's a pretty big difference from before. However, if I have an equation, I can actually solve for x. I can algebraically figure out what number or numbers would make this work. And again, everything I'm saying is distinctly different from what we've been dealing with before. And so while most of this unit is dealing with expressions, factoring expressions, multiplying expressions, dealing with rational expressions, equations are nothing new either. And so how do we solve a rational equation? Well, pretty much like how you solve any other equation. And you've been solving equations for years. The main difference here is that, I got some fractions. And it'd be kind of nice if this denominator of t and this denominator of 2 were not there. Well, I can get rid of them really easily. I can come up with an equivalent equation by multiplying both sides by the lowest common denominator. Now, why is that? Well, first of all, remember, if you're solving an equation, the whole idea of solving an equation algebraically is to apply inverses to both sides. You add a number to both sides. You divide both sides by a number. In this case, if I multiply both sides by 2 and by t, in fact, let me make that marker a bit bigger, something rather pleasant happens. Now first, where did 2t come from? Well, 2t is the lowest common denominator. So I'll make that little note here. 2t is the LCD. And again, we have to find those sort of things when we added or subtracted rational expressions. So that phrase, lowest common denominator, we've been dealing with that lots. But notice, if I multiply both sides by 2t, on the left-hand side, I can just cancel these t's out, which means I no longer have that denominator there, as long as I multiplied both sides by t. And similarly for the 2, if I can cancel out those 2's there, as long as I multiply the other side by 2. And so in the end, if I multiply both sides by the lowest common denominator, what do I have left? I have 2 times 3 times t minus 1, or really 6 times t minus 1, equals 3 times t. And this equation here is different than the equation I started with, but it's equivalent, which means if I can solve for t here, I'll find the answer to this equation. And this equation here, I think, is much more pleasant. And so that's, at this point, there's nothing really new to this anymore. Now we're just building on things you've learned from the last several years of math courses solving equations. And it all comes down to applying inverses to both sides, which I've already done. I multiplied both sides by 2 to get rid of dividing by 2. I multiplied both sides by t to cancel out dividing by t. At this point here, I'm going to use the distributive property to distribute the 6. 6t minus 6 equals 3t. I'm going to subtract 3t from both sides. You could also subtract 6t from both sides, but I usually recommend subtracting the smaller of the two variables if you have variables on both sides. That leaves me with just a 0 on the right-hand side and 3t minus 6 on this side. Add 6 to both sides. I have 3t equals 6. Divide both sides by 3, and you get t equals 2. Now that's it. All those last steps I did are nothing new. Now, I will say in a course like this, Pre-Calculus 11, After a while, I'm going to stop writing this stuff down in red that I put here. I'm going to stop showing explicitly what I'm adding or subtracting or dividing or whatever both sides by. But since we actually haven't really solved any equations so far until now in this course, I think it's beneficial for me to explicitly show those steps. But yeah, there we go. T equals 2, which means this original equation here is only correct. 3 times t minus 1 over t will only equal 3 over 2 if t equals 2 itself, which is very different from, an expression where essentially, unless there's a restriction, you can just replace the variable with whatever you want. All right, let's look at this. Oh, it looks mean, doesn't it? Well, it's not as mean as it looks. Again, though, I want to, as soon as I can, I want to cancel out all these denominators by multiplying by the lowest common denominator. And like before, once I get to that step, like equivalent to this step right here, then once I'm no longer dealing with denominators, then it's a matter of just building on things we've done for several years in math courses. So how do I find the lowest common denominator? Well, that should sound familiar. We first see by looking at the factors, and I can factor these two denominators here. So that's the difference of squares. And here I can take out a GCF. All right. Now, I'm not actually going to make all these denominators the same. I want to find the lowest common denominator and multiply everything by that lowest common denominator. And so what is the lowest common denominator here? Again, builds on the things we've done from recent lessons. The lowest common denominator I can see is x plus 2 times x minus 2 times 6. That's the lowest common denominator. So I want to multiply everything by 6 and x plus 2 and x minus 2. It's going to look a little bit crazy here, but we have to have faith. And so, if I'm going to multiply everything by this lowest common denominator, the whole point is to cancel out my denominators. So it'll look a little bit messy here, but I'm going to take this 2 and I go times 6 times x plus 2 times x minus 2. This 10 times 6 times x plus 2 times x minus 2. And over here, 1 times, I'm running out of space, 6 times x plus 2 x minus 2. OK, yes, it's messy. But let's look at these individually. This first term here, I'm multiplying by x plus 2 in the numerator. I'm dividing by x plus 2 in the denominator. Why not cancel them out? Same thing for x minus 2. So really, in the end, what do I have left? I have 2 times 6, which is 12. Like I said, it looks messy, but as long as we just trust that if we multiply everything by the lowest common denominator, we should cancel out all our denominators. Just 12. I like the number 12. Over here, the 6's cancel out, the x plus 2's cancel out. What am I left with? 10 times x minus 2. And over here, the x minus 2's cancel out. Nothing else. What am I left with? 1 times 6, or 6 times x plus 2. And so, if I just kind of show what we've done so far, notice, yeah, it looked a little bit kind of weird right here. It looks pretty messy, but when the dust settled, that's pretty pleasant, I think, compared to what I started with. And at this point, this is now, this is a tough grade 9 question, which means we can do this. We don't want to make a silly mistake, which we'll always do if we rush, but we can do this. I'm going to distribute the 10, distribute the 6. I can do a number of things. I'm going to subtract 6x from both sides, and I'm going to combine these like terms together. Do a few things. So on the left-hand side, I have 10x minus 6x, which is 4x, minus 8 when I combine 12 and negative 20 together. On the right-hand side, I just have 12. OK, I'm now going to add 8 to both sides. And so 4x equals 20. And notice with each passing step, my equation gets simpler and simpler and simpler. You can probably see the answer right now. But if I'm not sure, I can divide both sides by 4. So x equals 5. So notice how quickly things came together once I canceled out my denominators. And really, again, my idea was from here, I looked at that and go, I don't like all those denominators. I have an equation right? I have the left side that equals the right side, so I can kind of do whatever I want as long as I apply the same operation equally to both sides. In this case, I multiplied everything by 6 and x plus 2 and x minus 2, which canceled out all the denominators. If I didn't factor right away, I probably wouldn't have found the lowest common denominator so quickly. All right, that leads me to the final problem. For this question here, this may look kind of actually easier than the last one, but something kind of different is going to pop up, which leads us to the very last lesson in this unit. It's hard to really tell till we do it. So let's solve this. And so, like I said, at first glance, this looks easier, and it may still be easier than the last question. So first thing I want to do is find my lowest common denominator, which I can just see the lowest common denominator is going to be 4x. So I want to multiply everything by 4x. Multiply this times 4x. Multiply this times 4x. Multiply this times 4x. And so if I look right here, the 4 cancels out. And so what am I left with? Just x times x, or x squared. OK, let's look right here. The x's cancel out. So what am I left with? Just 7 times 4, so 28. And on the right-hand side, nothing cancels out. It's just 3 times 4x, which is 12x. All right, that's pretty nice. X squared minus 28 equals 12x. So what do I do next? Well, you may be tempted to subtract 12x from both sides. You may not be tempted either. Because at this point, or even the step before it, unless you've taken this class before, or unless you've had some supplemental instruction before, you haven't really solved an equation like this before, where we have x squared and an x. We have the same variable being squared and not being squared, just to the power of 1 in the same equation. So how do we solve this? I will say if there was no minus 12x, you've done this before with the Pythagorean theorem. For example, I could add 28 to both sides and say x squared equals 28. Then x equals the square root of 28. At least stuff like that should sound a bit familiar. If I didn't have the x squared, then it's a grade 9, grade 8 question. But put it all together, what do we do? Well, my first hint, if you would like a hint, is factoring this is going to be helpful. And the fact that it equals 0 is helpful as well. So let's factor this. And what are two numbers that multiply to negative 28, but add to negative 12? It may seem like you can't do it, but you can with negative 14 and positive 2. So how does it help me, though? Well, once I have this factored and it equals 0, this gets to a really fundamental idea of this course that we're going to start seeing a lot in this course and all future math courses. And it all gets built on the simplicity of the 0 times table. I have a factor times another factor equals 0. Well, the wonderful thing about equaling 0 is that once one of these factors equals 0, the whole thing equals 0. Right? 5 times, if I said 5 times something equals 0, what's that something? Well, 0. Nothing else can be right. If I said 15 times something equals 0, again, that wouldn't really matter. As soon as that equals 0, everything equals 0. And we can use that nice, simple, pleasant fact about the 0 times tables to our advantage. Because if I inspect this one factor right here, I can see if x equals 14, 14 minus 14 is 0. That means this whole factor here will become 0. And it'll be 0 times x plus 2. I don't even care about that because 0 times anything equals 0. And that's what we're trying to figure out. We're trying to make this whole thing equal 0. Which means I can now tell by looking at my factors by inspection that one of my solutions must be 14. And if you're not sure, you can take that 14 and put it back in here. And go 14 squared minus 12 times 14 minus 28. And if you don't believe me, you'll get a 0. That's it. Why don't you believe me? Anyways, I can do the same thing right here. I can look at this factor by inspection, and I can realize, OK, if x is negative 2, negative 2 plus 2 is 0. And once this becomes 0, I don't really care about this factor here, because 0 times anything equals 0. And that's our goal. It's explicitly stated right in front of us. We're trying to make this equal 0. We're trying to solve for x so that this whole thing equals 0. So I can see my two answers. So my solutions are x equals 14 and negative 2. This equation has two solutions, which means if I replace x with 14 or negative 2, and I bring it back to my original equation or any of the other equations below, the equation will work. If I pick any other number, it won't. And notice what I did here is I solved an equation using factoring, which is a new idea, and I got 2 solutions. And this is one of those, perhaps the first time you've seen an equation that you solve that has 2 solutions. This idea is going to become a fundamental theme of this course. And really, this is going to be the focus of the next and last lesson in this unit. But for now, I think I can stop.